Quantum Computing, Qubits Newsletter, June 2025. News: the quantum computing landscape experienced remarkable acceleration throughout 2024 and early 2025, marked by groundbreaking achievements in error correction and unprecedented investments from both private and public sectors. Google's Willow chip demonstrated quantum error correction below the surface code threshold, performing a benchmark computation in under 5 minutes that would require the world's fastest supercomputers 10 septillion years to complete. This milestone represents a fundamental shift from theoretical possibility to practical reality in quantum advantage. IBM continues its aggressive roadmap execution, unveiling plans for a quantum-centric supercomputer by 2025 with over 4,000 qubits. Their Flamingo processor, scheduled for deployment through 2028, will progressively scale from 156 qubits and 5,000 gates in 2025 to 15,000 gates by 2028. The company's focus has evolved beyond mere qubit count to emphasize circuit quality and gate fidelity, with their Heron processor achieving significantly improved error rates while maintaining practical utility. Harvard University, MIT, and Quira Computing achieved a major breakthrough by demonstrating quantum error correction on an atomic processor with 48 logical qubits, marking the first practical implementation of fault-tolerant quantum computing at scale. This development, recognized as Physics World's 2024 Breakthrough of the Year, validated that quantum processors can suppress logical error rates exponentially as the number of physical qubits per logical qubit increases. The investment landscape remained robust despite broader technology sector challenges. Private and corporate funding for quantum technology startups reached $1.2 billion in 2023, defying a 50% decline in overall tech investments. The majority of funding, 62%, flowed to companies founded 5 or more years ago, indicating a shift toward more established quantum firms with proven technologies. Public sector investment exceeded $42 billion globally, with significant new commitments from Germany, the United Kingdom, and South Korea leading the charge. Microsoft and Quantinuum achieved an unprecedented milestone in logical quantum computing, creating 4 logical qubits with only 30 physical qubits and performing 14,000 individual quantum circuit instances without errors. This breakthrough challenges conventional assumptions about resource requirements for fault-tolerant quantum computing, where it was previously estimated that hundreds or thousands of physical qubits would be needed for each logical qubit. Quantum computing trends. The quantum computing industry is experiencing a fundamental transition from the noisy intermediate-scale quantum (NISQ) era toward fault-tolerant quantum computing. Major consulting firms including McKinsey, Deloitte, Boston Consulting Group, and Accenture have identified this shift as accelerating practical applications across multiple sectors. McKinsey's latest quantum technology monitor reveals that 4 sectors, chemicals, life sciences, finance, and mobility, are positioned to see the earliest quantum computing impact, with potential gains reaching $2 trillion by 2035. Entanglement remains the cornerstone challenge in scaling quantum systems. Recent breakthroughs in materials science have revealed new approaches to achieving stable entanglement states. Researchers at Columbia University developed a novel quantum refrigerator that can autonomously cool superconducting qubits to record low temperatures using just 3.4 micrometers of stacked molybdenum disulfide crystals. This represents a 100-fold improvement in efficiency compared to previous methods while enabling on-chip integration for practical quantum devices. Rice University physicists made significant progress in understanding quantum entanglement in strange metals, materials that defy conventional physics. Using quantum Fisher information, they discovered that electron entanglement peaks at quantum critical points, providing new insights into the fundamental mechanisms that could enhance quantum computing materials. These findings suggest that strange metals could play a crucial role in future quantum technologies where enhanced entanglement is essential. Cooling requirements continue to pose significant engineering challenges. Most quantum computers require temperatures between 10 and 100 millikelvins, colder than deep space, to maintain quantum coherence. Recent innovations include thermally driven quantum refrigerators that achieve 99.97% ground state probability for qubits, significantly improving on previous techniques that achieved 99.92%. Researchers are exploring helium-free cooling using supersolid materials and immersion techniques to reduce the complexity and cost of cryogenic systems. The debate between qubits and qudits is gaining momentum across the quantum community. Qudits, quantum systems with 3 or more states, offer the potential for more efficient calculations and reduced error rates. Researchers at Innsbruck University successfully used qtrits and qquints to simulate high-energy quantum particle interactions, demonstrating that qudits can pack more information into each computational unit. However, qudits also introduce increased complexity in control and measurement systems, creating trade-offs that must be carefully evaluated for each application. Error correction has emerged as the defining challenge for practical quantum computing. The development of surface codes, color codes, and novel distributed quantum error correction schemes represents the industry's most critical research frontier. Google's Willow chip achieved a lambda factor of 2.14, meaning logical error rates decrease as code distance increases. While this represents significant progress, experts estimate that lambda factors of 10 or higher will be required for cryptographically relevant applications. Industry roadmaps from major players reveal an ambitious timeline for quantum advantage. IBM targets fault-tolerant quantum computers capable of executing 100 million gates on 200 qubits by 2033. Google aims for 101,000 logical qubits by 2030, while Boston Consulting Group predicts enterprise-grade quantum applications achieving positive return on investment could emerge as early as 2025-2026. The emergence of quantum-centric supercomputing represents a paradigm shift in computational architecture. Rather than replacing classical computers, quantum systems are being designed to work synergistically with traditional high-performance computing resources, creating hybrid platforms that leverage the strengths of both technologies. Quantum computing recommendations. Organizations must begin quantum readiness initiatives immediately to position themselves for the coming transformation. Deloitte's research indicates that 25% of Fortune 500 companies will be using quantum computers within 3 years, making strategic planning essential. Companies should establish quantum centers of excellence that combine business strategy, technical expertise, and risk management capabilities. The cybersecurity implications of quantum computing demand immediate attention. Current encryption methods, protecting trillions of dollars in daily internet transactions, will become vulnerable to quantum attacks. Organizations should implement post-quantum cryptography standards developed by NIST, beginning with an inventory of cryptographic assets and high-risk datasets. The concept of harvest now, decrypt later means that sensitive data encrypted today could be compromised when quantum computers become sufficiently powerful, making the transition to quantum-resistant security urgent. Investment strategies should focus on quantum-ready applications that can deliver near-term value while building long-term capabilities. McKinsey's analysis suggests optimization problems, machine learning acceleration, and molecular simulation offer the most promising early applications. Financial services firms should explore quantum-enhanced portfolio optimization and risk modeling. Chemical and pharmaceutical companies should investigate quantum molecular simulation for drug discovery and materials development. Manufacturing organizations should evaluate quantum optimization for supply chain management and production scheduling. Talent development represents a critical bottleneck that organizations must address proactively. McKinsey research indicates fewer than 50% of quantum jobs will be filled by 2025 unless significant changes occur in talent development or job creation rates. Companies should partner with academic institutions to develop quantum education programs and recruit from physics, computer science, and engineering disciplines. Cross-training existing technical staff in quantum concepts can help bridge the skills gap. Technology partnerships will be essential for most organizations entering the quantum space. Rather than building internal quantum capabilities from scratch, companies should leverage cloud-based quantum computing platforms from IBM, Google, Microsoft, and other providers. These platforms allow experimentation with real quantum hardware without the massive infrastructure investments required for on-premises systems. Risk management strategies must account for quantum's dual nature as both opportunity and threat. While quantum computing promises transformative capabilities, it also introduces new vulnerabilities and regulatory compliance challenges. Organizations should develop quantum risk frameworks that address cybersecurity, operational resilience, and competitive positioning. Industry collaboration will accelerate quantum adoption and standardization. Companies should participate in quantum consortiums, standards bodies, and research partnerships to influence technology development and share best practices. The quantum ecosystem benefits from collective advancement rather than isolated development efforts. Experimental programs should begin with well-defined pilot projects that can demonstrate quantum value without requiring fully fault-tolerant systems. Current NESQ devices can provide valuable insights into quantum algorithms and use cases while building organizational quantum literacy. These experiments should focus on problems where quantum approaches offer clear advantages over classical methods. Regulatory preparation is becoming increasingly important as governments worldwide develop quantum policies and standards. Organizations operating in highly regulated industries should monitor quantum-related regulatory developments and ensure compliance frameworks account for quantum technologies. The intersection of quantum computing with data privacy, national security, and international trade will create new compliance requirements. The quantum revolution is no longer a question of if, but when. Organizations that begin preparing now will be positioned to capitalize on quantum advantages, while those that delay risk being disrupted by quantum-enabled competitors. The convergence of breakthrough hardware achievements, substantial investments, and practical applications creates an unprecedented opportunity for forward-thinking leaders to shape the quantum future. The next 5 years will be defining for quantum computing's commercial viability. Companies that establish quantum strategies, develop relevant capabilities, and forge strategic partnerships today will be best positioned to benefit from the quantum transformation that is rapidly approaching. The time for quantum readiness is now.